All right, so this is Unit 4 review. Determine if the graph is one-to-one. One-to-one, you just do the horizontal line test. If it touches in more than one place, then it is not one-to-one. So this one does only touch that graph in one place, so it is one-to-one. Right here, you can draw it anywhere. If it touches in two places, it's not a very good line, but if it touches in two places, it is not one-to-one. And then the last one, again, you can draw your horizontal line anywhere on this graph. If it touches in two places, then it is not, or more, okay? It is not. It can only, in order to be one-to-one, it can only touch the graph in one place, just like the vertical line test. Okay, so now, and what one-to-one means is it has an inverse. So now it says determine algebraically whether the two functions are inverses by using composition of functions. Okay, I hope I have enough room in here to work this. I think I do. All right, so basically what the composition of functions is, we're first going to do f of g of x. Now, the key thing is algebraically. Okay, you've got to do it algebraically. What this means is you are going to take your g and you're going to substitute it into f. So you take your f function, which looks like 3 times whatever x is minus 2. Okay, that's the function, 3x minus 2. My x in this case is this right here. So I put that in wherever I see an x into the function. What I'm doing is I'm taking that and I'm plugging it right there. Now, you clean the problem up. So you're going to distribute the 3. 3 times 3x gives us 9x. 3 times 2 gives us 6 minus 2. So we're going to end up with 9x plus 4. Okay, because we only had to do the composition, you have to do the composition the other way as well. But in order for them to be inverses, this here has to leave us with x, not a negative x, not a whatever. It doesn't matter that the two match at the end. See, I'm not going to do the second part. Well, I will for the review. If I do the other composition of function, okay, where I'm going to take my f and I'm going to plug it into g. Okay, so that means I take my g function, which says 3 times whatever x is plus 2. Okay, well, now I'm taking this function and plugging it in there. So I get 3x minus 2. All right, so I'm taking my f and plugging it into g. When I finish this up, when I clean it up, I get 9x minus 6 plus 2, which gives us 9x minus 4. See, this one did not end up with just x, okay? You really only have to do one of them if it's not. If it does end up to be x, then you must do the other one just to make sure. So this one, these are not inverses. So not inverses. And again, you only had to do one of them. You didn't have to do both because the first one didn't end up with x. Over here, I'm first going to do f of g of x. Then I'm going to do g of f of x. Now, again, if they are inverses, both of these will end up to be just x. Okay, can't be anything else, not a negative x, not x plus 2 on both of them. All right, so what I'm going to do is I'm going to take my g function and I'm going to plug it in for f, into f. So I'm taking this right here and I'm going to put it right there. So I take out my x and I put 5x plus 4. I still have my minus 4 all over 5. That cancels, so I have 5x over 5. Well, 5 divided by 5 gives me 1x or just x. Okay, so far, they're inverses. Well, in order to determine it, I also have to do the other where I take my f function and plug it into g. So I'm going to take this and plug it in right there. So I'm going to have 5 times my whatever my x is plus 4. In this particular case, I'm taking that out and I'm plugging in x minus 4 all over 5. This here, my 5's will cancel because this is 5 over 1. One's in top, one's in the bottom. So I'm left with x minus 4 plus 4. Negative 4 minus 4 plus 4 gives me 0, so I am just left with x. Because both of these are x, these are inverses. And that's how I proved it algebraically. Okay. Given the graph of y equals f of x, sketch its inverse. Remember, that's not -1. That is the inverse of f. All right, so what you got to do is you got to pick some good points on here, okay? I'm going to pick, and when I say good points, it's ones that are right in the corner of a square. This point right there is 10, 9. All right. I don't know if you just got to pick some. I would pick some up here. I definitely would pick that one because that one's easy. And then I'd pick some down here. I'm just going to pick another one right here. You probably only need 3 points, but I'll pick this one as well. 1, 2, 3, 4, 5, up 1, 2, 6, 7. So that is 5, 7. That one is 0, 4. Let's pick this one here because that one looks like a good point. That one is 2, oops, -2, 0. And then, I don't know, I'll pick this one right here. Why? I don't know, it's in the corner. I wouldn't want to pick this one here because that's not in the, it's not, whoops, it would help if you could see it. I'm not going to pick this one right here because it's not in the middle, it's not right in that corner. Okay, and that point there is -6, -10. So when you are going to do the inverse, all you do is you switch your x and your y. So this becomes 9, 10, 7, 5, 4, 0, 0, -2, and -10, -6. And then we graph these. 9 up 10, that would be, this goes out to 10. So 9 up 10 is right here. 7, 5, up 1, 2, 3, 4, 5 right here. 0, 4, 1, 2, 3, 4 right here. I've messed up someplace it looks like right there. That point doesn't line up right there. Let me see if that one's right. 1, 2, 3, 4, 5. Up 1, 2, 3, 4, 5, 6, 7. So 7, 5. 1, 2, 3. I guess so. Maybe it's just I'm not looking at it right. Okay. If not, just pretend. All right. 0, -2 right there. And then 10, -10, -6. 1, 2, right there. Now, when you connect these, this goes like this. Don't have a straight edge right there. And then it goes like this. Okay. And what happens on this is it reflects around this y equals x line, like 1, 1, 2, 2, 3, 3, all the way up. It reflects around that. Okay. So the top look like the bottom, it mirrors it. Okay, right here, I'm not going to pick as many points. I'm going to pick this one right here, which is -7, 3. Okay, let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, this one here. Okay, I pointed to that one. I meant this one. This one's a good point. That one is -2, 0. I'm going to pick that one. That one's a good point. It is 0 down, -5. And then the other one I'm going to pick is 8. 1, 2, 3. 8. Down 1, 2, 3, 6. That point right there is 8, -7. So when I do the inverse, I just switch my x's and my y's. So it's 3, -7, 0, -2, -5, 0, and -7, 8. So I'm going to graph those points. Right 3, 1, 2, 3, down 7. And I'm going to graph this in purple because that graph is in blue. I mean in red. You probably, I don't know if you can see it's in purple. Okay, then 0, -2, that's going to be right here. So I'm going to connect those two. Then -5, 0. So I'm going to connect those two. And then -7, 8. It's right there. Okay, and again, it reflects around this y equals x. Okay, all right, that's how you do graph the inverse. You just flip the x and the y's. All right. Now they are telling you that it's 1 to 1. Again, that means we have an inverse. So what we're going to do now is find that inverse. There's 4 steps to it. First step, take your f of x out, replace it with y. Second step, switch your x and your y. Third step, solve for y. So we're going to subtract 2. And we get x minus 2 equals 7y. Now divide by 7. And we get y on this side, and we get x minus 2 over 7. You can put x over 7 minus 2 sevenths. It doesn't matter. Okay. Now what we're going to do, the last step, is just replace this with the correct notation of the inverse of f of x. I'm just going to put it first, is equal to that. Now, if you take this, plug it into here, you'd end up with x. If you take that, plug it into here, you'd end up with x, and you know it's right. Right here, we're going to now do g of x. Take out your g of x, replace it with y. Switch your x and your y. So x goes here, y goes here. Solve for y. We're going to add 3. And we get x plus 3 equals y cubed. All right. The inverse of y cubed is cube root. So you're going to take the cube root of both sides. Cube root cancels cubed out, so you left with y. And on this side, you're just going to have the cube root of x plus 3. Now we do the correct notation for our inverse, which is going to be g, the inverse of g of x, equals the cube root of x plus 3. Don't forget about your little 3 there. All right, excuse me. Right here, same steps. Replace that with y. Switch your x and your y. Now we got to solve for y. Because this whole thing is underneath that radical, we need to get rid of that radical. We need to get rid of the square root. The opposite of the square root is square. So I'm going to square both sides. So I get x squared equals y minus 5, add 5 to both sides, and we get x squared plus 5 equals y. Now do the correct notation. It was called h, so we're going to do the inverse of h of x equals x squared plus 5. Okay, this one probably, no, this one's not too bad. Okay, we're going to put a y, replace it with y, f of x with y. We are going to solve for, we're going to switch our x's and our y. Now we have to solve, whoops, I forgot to change it to a y. Y minus 2 on the bottom. We have to solve for y. There's a couple of different ways of doing this. I just get rid of my denominator by multiplying by the denominator of y minus 2. You can cross multiply. You can get them to have the same denominator, then ignore the denominator. It all works the exact same way. Okay, this is over 1. And I'm doing that. I put it in parentheses so you know you can't like split that up. That will cancel that out, and I'm left with 3 on that side. Over here, I'm going to distribute. Oh, yeah, I'm going to distribute the x. So I get y times x is xy, and x times a negative 2 is a negative 2x. Now we have to solve for y. Well, I need to get this by itself first. I need to isolate that. So I'm going to add 2x to both sides. I'm just going to put that next to it because we can't add those anyway. They're unlike terms. And we have xy equals 3 plus 2x. Now to get y by itself, we divide by x. So we are going to get y equals 3 plus 2x over x. We're going to use the correct notation, which this is called f. So we found the inverse of f is equal to 3 plus 2x over x. You could write this as 3 over x, because that's what that gives us right there. And that would simplify to just 2. Okay? Both of these are the exact same thing. So if I divided this by x, I still get 3 over x. If I divide 2x by x, I end up with 2. So either way is fine. All right, number 5. Find the domain and range of the following inequality notation and in interval notation. Okay. Right here, this is an exponential. Okay. So exponential functions, the domain is all real numbers, which means it's negative infinity to infinity. Okay. Right here, if you were to graph that, it would move that graph down 3. Your range, so let's show it to you on a graph, because that's what most of you are going to do. See if I can get out the glare. You're going to say, let me get rid of that, 2 raised to the x power minus 3. And it looks like this. You have a horizontal asymptote at negative 3. Okay, it doesn't touch negative 3. It looks like it does on our graph, but if we actually filled it in, you'd never actually get to 3. So our domain, and notice, or I'm sorry, our range is our y values. We do not use anything less than negative 3. So our range in this particular case, the inequality would be x is greater than negative 3. It can't be equal to it. Can't be equal to it. Because that's where that horizontal asymptote is. So to do interval notation, it's negative 3 to infinity, okay, with parentheses. This one right here Okay, our domain, let's see if I'll squeeze it in over here because that problem up above, I was going to put it there, but that's in the way. The domain for this graph, this looks like it's on, well, actually, I'm sorry, domain, it's an exponential, so it's negative infinity to infinity. We use all our x values. The range is what changes. The range only goes up to this 5. There's actually a horizontal asymptote at 5. That it's just because of the pixels, it's a pixel problem here, okay? It doesn't touch that 5, it approaches it. But we use all of these values down here. So negative infinity up to 5, but it doesn't actually, it approaches 5, but it doesn't touch it. Oh, and if you're doing, sorry, I'm so used to doing interval notation. This here, all real numbers. This one right here would be x is less than 5. All right. Write each equation in exponential form. This is where we use the circle of logs. We start with our base. This is our exponent, gives you our argument. So you say h to the s power equals x. Right here, this is our base. This is our exponent. So it's p to the f power equals that, our argument, 2 plus x. Right here, k to the c power equals b. Pretty easy, should not be difficult. Okay, now we're going to go backwards. We were going from here to here, now we're going to go here to here. All right, so let's use log. Okay, and just fill in what we know. We know the base goes here. Okay, it's a little baby number. The exponent goes on the other side of the equal sign, and this is our argument. Okay, you can even check it by doing circle of logs. Y to the x power equals d. Okay, this one right here, there you could do two different ways, but we usually just write it one way. Okay, if you were going to use log, I'm going to put it right here. This isn't the way I would want it, okay? I don't think we were going to want it this way. But it'd be log to the base E. Our exponent goes here, and our argument goes here. E to the x power equals 7, okay? But the only thing about that is we have a shortened version of this, which is the natural log. We don't need to write it out that way. So it's natural log of 7 equals x. We know it's a base E. Right here, log base C. Our exponent goes over here and our argument goes here. Log base C of x equals B. Okay, and I'm going to stop right there.